theory of the universe was the most popular theory of the universe at the time was that the universe was eternal, never changing, static. This wasn't the case, as it turned out. Now, George Lemaitre was a Catholic priest, and he was interested in general relativity. He was also a scientist, so he was interested in general relativity for that reason. But his immediate thought was, what if I try to do general relativity in terms of the universe? And he plugged it in and came out with this result that the universe cannot be static. And he showed this result to Einstein, who didn't believe him at first. And then once Einstein was convinced, he modified his theory to prevent this from happening. He added an extra term to the equations so that you could get static universes again. And later in his life, Einstein called this his greatest blunder. The reason he called it his greatest blunder comes from this guy, Edwin Hubble, who was an astronomer. He worked at Mount Wilson Observatory. As you can, this is an image of him looking through one of the telescopes at that observatory. And Hubble was the first person to realize that there was stuff beyond our own galaxy, that there are other galaxies, in fact. But the thing he's most famous for was observing what are called Cepheid variable stars. These are stars that pulse in a predictable way. So and also the brightness and the frequency of their pulsing are correlated. So we know how bright a Cepheid variable star is by the speed at which it pulses. And if you know how bright something is, you can tell how far away it is, because you know how bright it should be, and then you see how bright you actually observe it, and you compare the two, and then you can say, oh, well, it's this much dimmer than I expected, so it must be this far away. So Hubble did this, and he also measured the Doppler shift of the star. So you can measure how, by the color of the star, you can measure whether it's moving towards you or away from you. It's exactly the same principle as when you hear like an ambulance come towards you and it gets like higher and higher pitch. And as it's going away, it gets lower and lower pitch. It's the same idea, but with light. And so Hubble took this, and he took the Cepheid variable stars, and he measured how far away they were, and then whether they were moving towards us or away from us, and how fast. And what he found was something really incredible, which I'm showing in this reproduction of his figure on the right here, which is that the further away something was, the faster it was moving away from us. So all of these stars were moving away from us, and the further away they are, the faster they're moving. Now, this is really surprising. I mean, how could you possibly explain something like this? The way that Hubble didn't know it at the time, but there was an explanation that it came from the work that Lemaitre had done with Einstein's theory. And the way it works is something like this. If you have space, just pure empty space expanding at a constant rate, which you can happen in general relativity. Stuff can evolve, space and time can evolve and warp and shift. Space itself can grow. New empty space can be created. If that happens, then, and it's happening at a constant rate, then there's more. If you're, say, 4 meters, say, or maybe a space unit is better, 4 light years away from something, then in each light year, space is expanding. And so you get sort of 4 light years worth of space, all of it expanding. And so the star that's 4 light years away from you looks like it's moving away at a rate of 4 times the rate of the expansion. If it's 8 light years away, then there's 8 chunks of empty space away from you, between you and the star. And so the star looks like it's moving away from you at a rate of 8 space expansions. So the way that you can get this is that everything is moving away from everything else. We don't occupy the center of the universe. It's not like everything is moving away specifically from us. Everything is moving away from everything else. And the way that And the way that you get this from the perspective of gravity is that each point in space is expanding at that rate, or at a constant rate, and then that constant rate for some point in space translates to a rate of expansion, a rate of motion with distant thing relative to distant things equal to the amount of space between you and that thing. So let's pause for a moment. If things are moving apart now, everything is moving away from everything else at essentially a constant rate, everything must have been closer to everything else in the distant past. Things must have been closer together. Those distant stars were closer to us in the past than they are now. And as a general rule, denser means hotter. If you've ever pushed gas into a tank, for example, like a scuba tank, then you know that that tank heats up. As you push more stuff into some region, it heats up. And so 13.6 billion years ago, roughly, everything was so close together, so hot and dense, that not even subatomic particles could form. That's what we call the Big Bang. And that is where the cosmic microwave background comes from. It's leftover heat and leftover light from that primordial time when everything was just this hot, dense soup. Now, I want to address some misconceptions about the Big Bang because there are plenty sort of floating around in the popular imagination. The first is that the Big Bang was not an explosion. It's not like there was a giant explosion of from some center, because there is no center of the universe. Then the Big Bang was not a point. The Big Bang happened everywhere, all at once. And it's also, sort of on a related note, the universe is expanding, but that doesn't mean it's finite. And it doesn't mean it's expanding into anything. Everywhere in space, like I said, new empty space is being created. So there's no edge really of the universe. The universe, it's not expanding into anything. It's just that space is growing. And so that could happen even if the universe were infinite, because what matters is that distances between stuff is growing. The distance between two things is growing. Even if there's infinitely many things, that can still happen. Another misconception about the Big Bang is, well, what came before? Well, we don't know, because at a certain point, we can't look further back in time, because everything is so hot and so dense that you can't peer further back. There's no instrumentation we have available that can extrapolate. But there's a few possibilities, which I'll list here for the sake of argument. The first, most obvious possibility is nothing. The Big Bang could be the beginning of time, in which case before has no real meaning. This is allowed by the theory of general relativity, but most physicists don't believe that's the case. Another option would be like a cyclic universe. Maybe the universe had contracted and now it's expanding again. That would be possible. So that would be called a big bounce. Another possibility is something called inflation or internal inflation, in which case there was another universe before this one, and the early universe that we think of as the Big Bang was sort of spawned from that. We can't tell. We have no idea which of these are correct. So this is all speculation, but these are some of the ideas that scientists have considered. And there's been so much amazing science that's been done regarding the Big Bang and the cosmic microwave background. As I showed you before, there's been amazing instrumentation that's looked at the cosmic microwave background in beautiful detail. And people have looked for what's called this power spectrum, which is like the oscillations in the cosmic microwave background, or the CMB. People have searched for primordial gravitational waves. People have looked for dark matter and dark energy. People have looked for trying to understand the shape of the universe. And people have also thought about two. I'm not going to describe these in much detail here, but if you're interested, ask me in the questions. People have examined two almost problems with the ideas about the Big Bang, which are called the flatness problem and the horizon problem. again, and these are actually what motivates, like in cosmic inflation in many universes, which I just mentioned. But I'm going to not talk about that for now. But if you're curious, ask later. So we talked about the beginning. What about the end? Well, so for the longest time, people thought there were three possibilities, which I've enumerated here, where the x-axis is time, the y-axis is current distance between stuff, and then these three curves are demonstrating what could possibly happen. And there were that people had considered. I will give you a hint now that it turns out that the real answer is none of these, as I'll show you in a bit. But what people thought, people categorize these as open universe, flat universe, and closed universe for reasons I'll show you in a minute. And open universes, the universe just keeps expanding at a constant rate forever. A flat universe, the universe decelerates, but eventually it doesn't collapse again. It just decelerates and then sort of becomes kind of static, as was imagined by Einstein with his correction terms. And then the final option is what a closed universe, where the universe decelerates and then collapses back in upon itself. And for a long time, scientists didn't know the answer. We do now, and I'll tell you the answer in a few minutes. But they wanted to understand it. And one way they thought to do it was that this open, flat, and closed universe, they actually relate to the shape of space. So an open universe, the shape is kind of saddle-like. Flat is what it sounds like. And this is, I'm saying flat, saddle, flat, open, and closed is more like spheres or a ball-like. But remember, you know, we live in 3D, not 2D. So you should think of if you can, the three-dimensional equivalent of this. And this is often understood in terms of angles. So in a flat universe, on a large enough scale, the interior angles of a triangle add up to 180 degrees. This is what we're used to. But in an open universe, they add up to less than that. And in a closed universe, they add up to more. And you can actually look for this in the structure of the cosmic microwave background. And I'm showing you on this plot here the patterns that one might expect from these three kinds of universe that you might see in the fluctuations of the light in the cosmic microwave background. But it turns out that if you do this measurement, which scientists did, the universe is extraordinarily flat. It's indistinguishable from completely, at large scales, completely flat. Obviously, on small scales, that's not the case because gravity exists. And so the curvature of space is distorted on small scales. But on the very largest scales, it appears to be flat. But it turns out that this ending of the flat universe on this plot that I showed you before, that's not where we're headed. And the reason for that comes, let's return to this Hubble experiment that Hubble did. People have now performed this experiment, not with Cepheid variables, but with supernovae. So there's a certain type of supernova, which is an exploding star called a type 1a supernova. This is a picture of one on the left. That's the Cat's Eye Nebula. Or is that Cassiopeia A? I can't remember. Anyway, that's a supernova. And it turns out the type 1a supernovae have a very similar structure to the Cepheid variables, not in the sense that they're at all the same object. They're not, but in the sense that the color of the supernova tells you how bright it is in a very predictable way. And so you can play the same game where you look out into the sky and you see a supernova, and you look for you look at the color first, the shape of the color to see its brightness, and then also to get from the color, you can extract the velocity via this Doppler effect. And if you do this, and by the way, as an aside, how cool is it that we've measured the expansion of the universe from exploding stars? I think that's pretty amazing. if you do this measurement, you get something very surprising. So this is a modern version of the ignore the curves, only pay attention to the dots, which are the data points. This is a modern version of Hubble's famous plot, where the x-axis again is speed, is distance, and the y-axis is velocity as moving away from us. And while Hubble's plot was a straight line, this plot isn't quite, right? It curves. So things very far away are still moving away from us faster than things closer, but not as fast as Hubble's measurement made. And that's not surprising. The supernova measurement can go much further. It's not surprising that Hubble didn't agree with this measurement, because Hubble's measurement is only at the very bottom corner of this plot, where it actually does look like a line. This is much further away than what Hubble could ever measure. But what is surprising is the shape, the fact that it curves down like this, because what that means is things very far away are not moving quite as fast away from us as Hubble would have predicted. And what does that mean? Well, looking far away is also looking back in time, because it takes light a finite amount of time to reach us. So the things that are further away from us in this plot are also older. What that means is that things are moving away from us at some constant speed now. The universe is expanding at some constant speed now, but in the past it was expanding, but more slowly. Things in the past were moving away from us less quickly than they are moving away from us now. So the expansion of the universe is accelerating. Well, so let's go back to this plot, right? This one. All of these plots, it's constant speed or deceleration. But the truth of the matter is, the average distance between stuff is going to increase exponentially with time because of the acceleration of the expansion. So why is this happening? Well, we don't know. We have no idea why this is happening. We just call this dark energy. And there has been a prediction that dark energy comes from a combination of quantum mechanics and general relativity. And you can, through various methods, try to estimate how strong dark energy is compared to other stuff. So this is sort of the famous plot of that. Our universe turns out to be made up, or like how strong dark energy is. If you imagine that it's an energy or a mass, if it's stuff, which we don't know, it probably isn't, it makes up like 73% of the universe. Dark matter makes up 23%. And the rest of normal stuff that we expect, that's the rest of it. It's like 5%. So dark energy, it turns out, is like the most dominant thing in the whole universe. And if you try to work out the strength of dark energy as predicted by quantum mechanics and general relativity as compared to what we actually measure, it was way off, like 10 to the 107 times too big. To give you a sense for how insane that number is, the number of atoms in the observable universe is to that number as a cat, like the mass of a cat is to the mass of the Earth. So this is called the vacuum catastrophe, or the worst prediction in the history of physics. Oh, sorry, is this frozen? No. This has been called the worst prediction in the history of physics, or the vacuum catastrophe, which, for the record, I think is an amazing band name. Okay, so I want to talk a little bit about what the expansion of the universe means as far as sort of the size of the universe that we can observe and what that implies at the end of time. So here I've got a picture of sometime in the past, some star or something emitted some light. And we're a little bit far away from that point in the light, from where the star emitted the light, but the light's headed towards us and we'll see it eventually. It takes time. Light travels at finite speed. But while the light is traveling, the universe is expanding. And so the point that from which the light was emitted, by the time the light hits us, that star is further away from us than it was when the light was emitted. And so the sort of maximum distance from which light can be emitted and then still reach us is called the particle horizon, or the cosmological horizon. And the universe, all the stuff within that distance, is called the observable universe. So there's sort of two things going on here, right? There's the amount of time since the birth of the universe. There's only been so much time since the Big Bang, 13.8 billion years ago. So you might think that something can only reach us if it was less than 13.8 billion light years away, since a light travels a light year in a year. That's how it's defined. But it turns out no, because that thing moved, we can actually see everything up to 90 billion light years away, which is where everything that was 13 billion light years away from us 13 billion years ago is now. But it's more complicated than that, because at some point, things will be moving away from us so fast that light can't get to us, even if those things are emitted within a distance that we should be able to see, because the light will just be pulled away with the universe. And so it'll never reach us, even if it's coming towards us as fast as it can. And this, my friends, is how it ends. So long after the sun has died and the Earth is gone, the universe will eventually expand so quickly that light from a distant star can't reach us. And what this means is that slowly, each of the stars, depending on how far away they are from us, in the night sky will blink out as they get too far away. And then eventually, when the night sky is totally dark, the expansion of the universe will keep getting stronger and stronger. And eventually, it will start to rip apart the atoms and molecules that make us up. And then everything, absolutely everything, will be diluted to nothing. And this is called the Big Rip. And that is how the universe dies. I am way early on time here, but that's what I have. So on that note, hopefully you have some questions for me and we can talk. Thank you.
Thanks, Jonah. You've given us a lot to think about, and probably people are trying to stretch their minds around everything that you've said. It is this entire subject is very mind bending, and it's hard. It's really hard to get your wrap your brains around the whole thing. I don't see any questions. Oh, here we go. All right. Is there a cosmic neutrino background?
Yes, there is. There's a cosmic background. There's a cosmic background for sort of every radiation carrier. So there's a cosmic neutrino background. There's a cosmic gravitational wave background in principle, and there's the cosmic light background, which we call the cosmic microwave background, because all the light is at the microwave frequency in the cosmic light background. So yeah, in principle, there's a cosmic neutrino background, and it matters. And I don't think it's something we can observe, but it's there. Great question.
And then tell us something about flatness and inflation. And I was going to point out actually that what you called almost problems, I mean, some people regard as serious problems.
Yeah.
and that's
right.
Exactly about flatness and inflation. So can you expand on that a little bit?
Yeah. So I call them almost problems because that's not, I wouldn't say that the word almost problem is in conflict with thinking of it as a serious problem. So the reason I called it an almost problem is because it's not in contradiction of the data, but it is still very surprising. So let me talk about both of these two almost, what I will continue to call almost problems, even if they're very serious almost problems. So let's first talk about the flatness problem. So I told you that we've observed that the shape of space is completely flat, and to whatever possible degree we could imagine. This is surprising because as the universe has been expanding, if there was even a little bit of curvature to the universe, if it was even slightly open, or slightly closed, then that would have been exacerbated as the universe expanded. It would have gotten more and more open or closed with time. And so for it to be flat now to an impossible degree, it would have had to be even flatter at the time of the Big Bang. And if you think about it, that means that there's, well, people think of this as a problem because they think, well, that's incredibly fine-tuned. What an amazing coincidence that the universe is exactly flat. If you that's the concern. How much of a concern you think that is, how serious you believe it to be, that depends on you. It depends on some people think it's serious, some people don't. It's actually, I mean, inflation is well accepted in the scientific community at this point, but it's not by any means uncontroversial. The horizon problem is it has to do with the cosmological horizons that I was telling you about before. But it's those cosmological horizons in the context of this, in the context of the cosmic microwave background. And so the fact that the problem here is that the cosmic microwave background looks the same everywhere, in every direction you could possibly imagine. Why is this surprising? Well, it's surprising because the stuff on the left, way over here, I don't know if you can, Galen, can you all see my cursor?
Yes.
Okay, great. Has never been in contact with the stuff on the right. They've never interacted. And so why should they look the same as each other? Them looking the same implies that like they've been mixed, that you could like, metaphorically, someone stuck a spoon in the universe and stirred, but that's impossible because there hasn't been enough time in the history of the universe for that stirring motion. So that's called the horizon problem. Is why is the universe as homogeneous as it is? And again, whether or not you consider this a problem depends on how disturbed you are by coincidence. You could say, well, why, if there's a coincidence like this, surely there's a reason. But maybe not. Maybe the universe just is this way. And we just have to accept it. So that's why it's both a serious problem and an almost problem. And cosmic inflation is one way of solving these issues by introducing, before the Big Bang, a period of extremely, insanely rapid expansion of the universe that means that before inflation, stuff could have been close to each other, and then it was ripped apart by inflation. And this also has the nice effect of undoing any kind of unflattening that you might imagine. It really flattens out space if you set it up right. But it's only hypothesized. Inflation requires mechanisms that have been unobserved, and it has implications that some scientists find disturbing. So it's I didn't want to present it to you. The reason I asked you to ask me in the questions rather than, and thank you for asking, Rick, rather than in the main talk, is that I wanted to emphasize that it's not observed, or at this point observable. That may change with time. I hope it will, and that we'll either see strong evidence for inflation or against, but that's not where we're at the moment.
It kind of strikes me as a mathematical trick that, without much physics.
Yeah, I think that's an objection people have. I am not personally, I've gone through phases. When I was in my PhD, I was pretty convinced by the arguments for inflation. I thought it was elegant and it made sense to me. As I've gotten a little older and more jaded, I'm now just less bothered by the problems in the first place. And I'm also just less interested in things that we don't have the technology to observe yet.
So other questions are, a follow-up on the neutrino background. What is its temperature?
Oh, yeah. So pretty sure it's the same temperature as the cosmic microwave background, which is 2.4 Kelvin. It's very, very close to absolute zero.
And about the gravitational wave background, does it have a temperature?
It does, and it's again 2.4 Kelvin. The gravitational wave background, interestingly, you might imagine that gravitational wave background would be harder to detect than the neutrino background, but it's actually the opposite. We can't detect either right now, but I think there's some hope that with like very advanced, very large and very sensitive gravitational wave detectors, we will be able to detect the gravitational wave background, which would be.
And so Rick Wallace asks how long the arms have to be in order to get the gravitational wave background.
Yeah, it's so it's actually for the gravitational wave background, it can actually be a terrestrial telescope, and the arms don't actually have to be that long. It's because the wavelength, it turns out, for the primordial gravitational waves is kind of the wavelength of a microwave. So what you need is a very, very sensitive detector with arm lengths of order like 500 meters to a kilometer. And so I think it's called the Einstein telescope, or no, it's called the Cosmic Explorer. If you look up this is a proposed terrestrial gravitational wave telescope that's supposed to be able to see primordial gravitational waves. There's actually been an experiment already, but it was nowhere near sensitive enough. It was called the holometer.
Another question, is there anything after the Big Rip, such as a recreation of a new universe, or is it just the end forever?
Yeah, that's a great question. So it depends on whether or not inflation is real, or, alternatively, other theories of quantum gravity. So there are a couple ways that you could imagine that the Big Rip isn't the end. One is if dark energy is not constant. Like, we know that the expansion of the universe is not constant. The universe accelerates. What if the universe isn't just, what if the acceleration itself is changing? In that case, you might eventually go the other way. We have no way to tell. And I don't think it's likely. Most people don't, but it's possible. That idea is called quintessence. And in quintessence, you could certainly get post Big Rip, or even a little bit before the Big Rip, you could get a big crunch and a bounce, or a big bounce, or some of these other ideas. The other possibility is the one motivated by eternal inflation. And so the idea here is that, so this requires a little bit of background. The idea behind the inflation, that sort of, if the universe is doing this crazy expansion, is that there's this particle called the inflaton, which has negative mass, and it basically powers sort of anti-gravity. And the inflaton usually doesn't exist, but permitted by the Heisenberg uncertainty principle, particles are just popping in and out of the universe all the time. Popping in and out of existence, I should say. It's not like they're popping into another universe. And if an inflaton pops into existence, then it will start a period of rapid inflation. But eventually the inflation will stop because of the structure of how this particle, well, the particle has to have a particular structure, a particular self-interaction to do this. And the inflaton has never been detected. We have no idea if it exists, purely theoretical. If the inflaton, but eventually inflation stops, and all the energy that was in the inflation and in these inflaton particles gets dumped back into a new hot gas, like the one at the beginning of our universe. And so you can imagine that from some place in our universe, post Big Crunch or whenever, inflatons might pop into existence and drive a new period of inflation, which would drive the birth of a new universe, and creation of a new cosmic microwave background. So that's the idea behind eternal inflation. Whether or not it's true, I don't know. Probably not. But that's certainly something people do take this idea seriously.
So I have a question about the observations of supernovae that gave rise to the current model of an ever accelerating universe. To what extent have people ruled out the possibilities that supernovae in the early universe were very different from supernovae in the current universe?
Yeah, that's a good question. This is something that has been considered regularly, and it's especially been concerning these days because there's the one can make a similar measurement of the acceleration of the universe from the cosmic microwave background, it turns out. And the cosmic microwave background observation does not agree with the supernova observation. They're different. They both predict accelerated expansion, but the number isn't the same. So then the question is, why don't they agree? Is it something to do with how we're modeling the cosmic microwave background? Is our understanding of the supernova wrong? Is it something like you're saying that the supernovae in the distant past were just different? I don't think this has been adequately answered, but I think it will be. So there's a new way of doing this cosmic, this sort of distance velocity measurement that I'm very excited about, which is, where did I put it? I got to find it in my slides again. Here, which is rather than looking at type 1a supernovae, look at neutron star mergers, kilonovae. So kilonovae are a little bit different. You can't get the distance to the kilonova from the brightness of the light, but you can get it from the brightness, or the loudness, I should say, of the gravitational waves, because the gravitational wave signal is very well understood, even though the glow from the explosion after these two neutron stars collide is not so well understood. But from that glow, you can still get a velocity measurement via the redshift, this Doppler effect. And so if we see enough kilonovae, neutron star mergers, we can get the distance from the gravitational waves and the velocity from the light after the explosion when they hit each other. And then we can have an independent measurement of this Hubble diagram, not just from supernovae, but from this other type of event. And then we'll really know. I mean, I think it's very unlikely, if the answer comes out the same, it's very unlikely that we're doing something wrong in both cases.